call is now being recorded.
Am I audible, guys? Hello? And my screen is visible, right? Yeah, thank you, Chandan. We'll wait for 5 more minutes, then we'll start today's session. Okay, guys, now we'll start today's session. So today we'll solve some problem based on pressure sensors and accelerometers. Okay, so first we'll start with basics. Right? So in spring mass system, let's say this is the fixed, this is a spring having a spring constant K, which is fixed to one end, and at the other end we have attached a mass M, and we are applying a force in. So when we attached a mass in a spring, the automatically the spring start stretched, right? This is the displacement x. Let's say this is displaced to this place. Now we know that for spring mass system, force is spring constant time x, where x is the displacement, k is spring constant, right? Also, force is nothing but a mass time acceleration, because that mass will accelerate if we attach its one point to the spring. So in equilibrium, we can equate these two forces, which is k times x and ma. So or we can say that in steady state condition, this is the correct word. In steady state condition, these two forces will be equal. So now if we want to calculate the sensitivity of this system, we can write it as x by a is nothing but this is capital M, yes, this is capital M by K, where displacement x is a measure of acceleration. If you are given with a spring mass system having a value of m and applied force in F Newton, you can calculate the sensitivity of the system using this formula. Right? Now we'll move on to some other concepts. Suppose now we'll talk about different pressure sensors. Pressure sensors. First is absolute pressure sensors. So if you calculate the absolute pressure this absolute pressure sensor measure pressure related to the related to the vacuum. Means here the reference is vacuum. We'll if we use absolute pressure sensor, then we'll take vacuum as a reference. Next type is gauge pressure sensors. Gauge pressure sensors. So in these types of pressure sensors, we measure the pressure related to the atmospheric pressure. Means in this kind of sensor, we will take a atmosphere pressure as a reference. Okay. Now the third and the last one is the differential pressure sensors. Last is differential pressure sensors. So these type of sensors measure pressure which is difference between two pressure sensors. As the name indicates, it is differential pressure sensor. So obviously it will measure a pressure which is different between two pressure sensors. Okay, so this is the basic types of pressure sensors. Now we'll move on to a pressure formula. Suppose we have This is a pressure sensor. This is a membrane. This is the port where we apply pressure. We call it as pressure port. This height is h and this distance is 2a, right? And this is some leads which is attached to the membrane. We call it as lead outs. Now if the membrane height is h and the length is 2a, then from theory of the plates, from theory of the plates, we'll write it as a pressure sensor. Yeah, so from theory of the plate, we can say that the pressure P is E times h to the power 4 divided by a to the power 4 multiply with 4.54 W naught by h plus 2.33 W naught h whole cube. This is a formula for pressure, right? Where W naught is nothing but a deflection. H is, as we can see in the diagram, is height. Two is the total length of the plate. Total length of the plate. So if you notice this equation, so this is some kind of, if we consider it as a x, this is x and this is x cube. So this is a non-linear equation. Means the pressure and the deflection are having a non-linear relationship. If this W deflection by h is too much less than 1, if we say, then we can ignore this cube term and we'll have P is h4 times a4 4.54 W naught by h. So this is a linear equation and the pressure, yes, we can say that this is a linear equation which shows linear relation between linear relation between pressure and deflection. Also here E is Young's modulus of elasticity. Okay, this is how you can you can rewrite this equation in terms of linear equations. Now, we'll move on to the pressure sensors. A piezoresistive sensors. And we'll do one derivation, and we will see what is gauge factor. Then we'll solve some problem based on this. Suppose we have a piezoresistive sensor sensor So let's say we have 4 resistor which is placed like this, and we call it as R1, R2, R3, R4. So when we form this resistor in a Wheatstone configuration, and taking output at here, this is applied input voltage. Let's say these two resistors will experience a same change in resistance, which is R plus delta R, and this will experience the same resistance of R minus delta R. Then from Wheatstone bridge we can say that R1 by R2 is nothing but R3 by R4. Then we can write as V now output is nothing but a V times del by R, which is nothing but a change in resistance. So output of this piezoresistive sensor is will be based on the change in resistance. Now we'll see one important formula. Suppose we'll study about stress or longitudinal stress. Suppose we have a square membrane it's not look like square, We'll again redraw it. So for square membrane having a side of 2A and this is the direction of longitudinal stress, then at x equal to plus minus a, because here the catch is this distance is a and this distance is also a. So at x is plus minus a, the longitudinal stress can be calculated as PA by h का whole square. So this is the formula for longitudinal stress. We are going to solve one problem based on this formula. Also, we'll talk about maximum stress. Usually what happens is the maximum usually what happens is the maximum or we can say that the maximum operating pressure is 1/5 of the worst pressure. Worst case pressure means this is a maximum stress condition. So the maximum pressure is always 5 times of, or we can write it as the burst pressure is 5 times of maximum operating pressure. This is the condition. Beyond this, your system will damage and won't work properly. Right? This is the condition for maximum operating pressure. This is the condition for burst pressure. Now, we'll solve the problem based on this burst pressure. So the problem is yes, what will be the burst pressure in megapascal for silicon membrane of site 500 micrometer and thickness 12.5 micrometer. If the maximum strength of silicon is 7 GPa, then what will be the maximum operating pressure? So now we solve this problem. First we'll draw the diagram. So here the catch is side is 500 micrometer. So This is 500 micrometer. Okay. Now we have seen the maximum stress is nothing but a maximum pressure times A by H whole square, right? So this is the condition for maximum operating pressure, because they have mentioned the maximum strength of the silicon is 7 GPa. It means they have given the maximum stress of 7 GPa, and this is the 2A, side 2, which is 500 micrometers. So if we calculate the value of A, that should be 250 micrometer, right? Now we'll put the values of sigma, which is the maximum stress, and the membrane side and the side of the membrane in equation 1. So from equation 1 we can this is 250 into 10 to the power minus 6. This is the height is, or the thickness h is 12.5 micrometer. This is 12.5 micrometer, the complete whole square, right? So if you solve this for maximum burst, for maximum pressure, you'll get a 17.5 megapascal, right? So we have solved, this is maximum operating pressure, right? Now in the problem they are also asking what will be the burst pressure, right? We know burst pressure is 5 times of maximum operating pressure. Oh, sorry, this is not a maximum operating pressure. This is burst pressure. Because this is the maximum limit for the material. Beyond that, we can't apply a pressure. We can't apply a stress. So for maximum stress, the value of pressure is called as burst pressure. So the maximum operating pressure is 1 by 5th times of 17.5 megapascal, or this is 3.5 megapascal. This is the maximum operating pressure, or which is 3.5 megapascal. If you compare these two values, you can clearly observe this as the maximum pressure is 5 times lower than burst pressure. So if you operate your sensor in this region, you'll get a required output. So this is how you can calculate the burst pressure and maximum operating pressure. Now we move on to the next concept. Now we first will learn about some concepts of capacitors. Capacitive sensors. So the capacitive sensor can be of three types. So this is a moving plate, and I'm drawing the fixed plate with blue color. Okay, and the motion is in this direction. Next, again we have one fixed plate, and this is moving plate. So in that case, the motion is in horizontal direction, right? Now, let's say we have a moving plate and also a fixed plate. Now, in third case, what will be changed? So in third case, dielectric will move. This is dielectric. So we can form a capacitive sensor using these three mechanisms, because you know the formula of capacitance, which is C is not is A epsilon naught by D. So we can vary the distance, which is a case A. We can vary the area B, and we can change the dielectric. This is the case third. So in that way, we can make a capacitive sensor. Either uh, they can be sensitive with distance, area, and dielectrics. Right now, we'll move on to the problem. Yes. So the problem is a parallel plate capacitor with 4 silicon support beam is shown below. The top plate has an area of 1 cross 1 square. The 4 support beams are each 500 micrometer long, 5 micrometer wide, and zero point 0.3 micrometer thickness. So what is the force constant Km experienced by the parallel plate capacitor? Uh, Diagram not drawn to scale. The Young's modulus of silicon is 120 GPa, right? So, very straightforward question. So, Km we can calculate it as by B h cube by 4L cube. If you put the value of this is B is 5 micrometer, H is 0.3 micrometer, divided by 4 times L cube. L cube is 500 micrometer. If you solve this, you will get some value, and the equivalent is 4 times of Km. So this is how you can calculate the value of Km. Now we'll see the formula for maximum strain. Maximum strain. Suppose we have cantilever beam which is fixed to the sand. The length is L, width is W, and thickness is T, right? And you are applying force at the free end of this cantilever beam. So for the maximum strain for the entire cantilever beam will occur at the fixed end of means that fixed end will experience a maximum strain. Now we can write the maximum stress in terms of torque is m, which is function of x times t by 2ei, where I is inertia, I is Young's modulus of elasticity, and m is the torque. Or we can simply write it as FL by LT 2ei, right? Because this the complete the point where the force is applied to the end of this free end of this beam. So the x is L. So the maximum strain is FLT by 2EI, where I is inertia. Now we'll see one more formula for gauge factor, which is a change, the gauge factor G is change in resistance by strain, right? Now, using this concept, we solve one problem. This is called a change in resistance if strain changes is called gauge factor. Okay. Suppose so we can calculate the gauge factor, right? Now solve one problem using silicon. The resistor is made by diffusion doping with a You didn't hear it strength is material. It will activity. Sorry for the interruption, guys. There was a problem with my server. Sorry for the interruption. Now we'll continue the problem. So in the problem, we have been asked to determine the percentage change in resistance if we apply a longitudinal force of 100 micronewtons. Right? So the gauge factor is given with 50, length is 200 micrometer, which is this one, width is 20 micrometer, and thickness is 5 micrometer, right? So first we will calculate, we know that the Young's modulus of elasticity Y is stress upon strain, stress upon strain, right? Then stress is force per unit area, force, and area we can write it as width times thickness. Okay, so here the force is 100 micronewton, width is 20 micro, and thickness is 5 micro. So if you solve this, you will get a stress of 1 megapascal. Okay, now we have calculated the value of stress. Using this, we can calculate the strain. So from equation 1, strain can be written as stress by Young's modulus of elasticity, which is given as 130 GPa. This is 130 gigapascal. Okay, so this is 1 megapascal and this is 130 gigapascal. So you'll get 0.00077. Now we have calculated the value of stress and the value of strain, right? So the gauge factor is, you know the gauge factor, G, which is change in resistance if strain changes, right? Or we can write it as del by R is nothing but G times a strain. Okay, if you put the value of G, which is 50, and the strain is 0.00077. Okay, so the change in resistance is 50 times 0.0385. It means if you apply 100 micronewton force in longitudinal direction the resistance will change by the factor of 0.0385. Just to verify this, let's say we have some initial value. We are assume the initial resistance was 10 ohm. Then change in resistance would be 10 kilo times so that would be 385 ohms. So this is how we can calculate the change in resistance if we apply a force in longitudinal direction. Now we'll solve one similar problem. So the question is, a fixed free cantilever beam is made of silicon crystal silicon. The question is same, but the difference is in the previous question we are applying a force in the longitudinal direction, but in that question we'll apply a force in the middle of the cantilever beam. So if we apply a same force in the middle of the cantilever beam, then what would be the percentage change of the resistance, right? So to solve this problem, first we'll calculate strain, the maximum strain, which we have seen one formula, which is m torque as a function of x times 2ei, or f times l t 2ei, right? So in this question the length is l by 2 because we are okay, or we can write it as f l t by 4 ei, where E is Young's modulus of elasticity and I is inertia, right? So we can calculate the value of I as bh cube by 12, where h is, or if we write in terms of width and thickness, that would be wt cube by 12. So we'll calculate the value of inertia using this formula, and then we'll put the value of I in equation 1. So W is, width is 20 micrometer. This is 20. Thickness is 5 micrometer. And this is 12. Okay. If you solve this, you'll have 5Q multiplied by 20 divided by 12, which is 208 into 10 to the power 24. Okay. So from equation 1, maximum strain is, force is 100 micronewtons. Length is around 200 micrometer. Thickness is 5 micrometer. And Young's modulus of elasticity is 130 gigapascal, same as the previous question. Yes, 130 gigapascal. Okay. And inertia we have calculated as 208 into 10 to the power minus 24. So if we solve this mathematical equation, we'll get a maximum strain of 0.019. 0.019. Now we know the gauge factor and we know the maximum strain. So the change in resistance which is del R by R can be written as gauge factor times this. So gauge factor is 50 and this is 0.019. This is around 0.95. Okay. So this is how you can calculate the change in resistance if we apply a force in different direction in the different way. Okay. Now we'll move on to some concepts. Now we'll solve some true false statement. So first is we have to answer it either in true or false. Okay. So the first question is, in general, sensitivity of a spring mass system based accelerometer is directly proportional to the lumped mass and inversely proportional to the spring constant of the system. Right? We have seen that in a spring mass system, the sensitivity is x by a, which is m times k. So that's not the directly mass is directly proportional. The lumped mass inversely to the spring constant. Yes, this This is directly proportional and this is inversely proportional. So the first statement is true. Okay. Now the second question is the sensitivity of the capacitive pressure sensor majorly depends on the ambient temperature. We know for the capacitive pressure sensors, the normal formula for capacitance is A epsilon by D. Or if you talk in terms of uh, displacement force for the transverse and longitudinal, this is again half CV squared by T. So we can see directly observe this. This is not depend on the ambient temperature. So yes, we can write it as the sensitivity of the capacitive pressure sensor won't depend on the ambient temperature. Okay, because in the one formula we have seen this, the capacitance is no way longer depends on the ambient temperature. Now the third question is the sensitivity of piezoresistive pressure sensor does not depend on the ambient temperature. So the name is piezoresistive. We know if the value of resistance changes, if the value of temperature changes, Sorry for the interruption, guys. Everyone with the server. So we'll continue. So we have seen question number 4, which is for commercial pressure sensors. The maximum operating pressure is usually 20% of the burst pressure, right? So yeah, this is true. Now the next question, fifth, is after the spin coating, usually baking or heating of the sample is used to evaporate the solvent. So yes, this is correct. After the spin coating, just to remove the excess coating material, we'll use baking or heating. So this is true. Now the next question is HNA is an isotropic agent. So as we have seen, this is not an isotropic agent. So this is false statement. Okay. Now, hey, am I audible, guys?
Yes, ma'am.
Okay, thank you. Now the next question is the ratio of strain and strain is known as Young's modulus of elasticity. So we know the formula. The Young's modulus of elasticity is stress upon strain. Stress upon strain, not the strain upon stress. Okay, so this statement is false. Now we'll move on to the question, the eighth question, which is a pull-in voltage for the parallel plate capacitor where the one plate is fixed and the other plate is able to move in a vertical direction does not depend on the area. Okay, so first we'll write what is the value of pull-in voltage. So we know what is pull-in voltage. So pull-in voltage is Vp, which is under root of 8 k d cube by 27 times a times epsilon naught, right? So they're saying the pull-in voltage for the parallel plate capacitor does not depend on the area. As we can see from the formula, it depends on the area. So this statement is false. Okay, now we'll see the gauge factor. So the gauge factor for the diffused semiconductor is lesser than the thin film metal. So we'll recall the table for gauge factors. So we know the gauge factor for metal foil. For metal foil, the gauge factor is 1 to 5. 1 to 5, right? Thin film, but thin film metal, it is around 2. For diffused semiconductor, it is higher, which is around 2080 to 200. And for polycrystalline silicon, it is around 30. So the question is, the case factor for the diffuse semiconductor is lesser than the thin film metal. So as you can see, the diffuse semiconductor is having a highest gauge factor, which is 80 to 200. So this statement is false. Okay. Now the last question is, high surface tension liquids are used in order to overcome the restriction during release of cantilever. So yeah, this is also a false statement. Okay, so this is how we have seen some true false questions based on the concept that we have learned. Now I'm going towards a spring mass system. So suppose we learn how to calculate the stability for accelerometers. So this is accelerometer. Okay, and we'll see the dynamic operation. So let's say this is a simple mechanical system. This is spring. This is one damper. And we'll attach a proof mass to the end of the damper and spring, and we are assuming the displacement is x in the direction of downward, and it will deflect to this point. So this is our spring and this is damper. Okay, now we know the equation which is we know the second order equation for this kind of system is m d square x by dt square b dx by dt plus k times x equal to f, or we can write it as ma, because force is nothing but a multiplication of mass and acceleration. So if you write it in terms of Laplace, we can write it as s square. We replace d square x by dt square with s square, dx by dt with s, and this is k equal to 0. This is the Laplace form of this equation. Or we can write it as x of s by as will be 1 by times s square plus b by ms plus k by m. Okay, where b is damping coefficient, m is mass, and k is spring constant. Okay, this is how we can write this equation. Now we know the equation, second order equation, or for equation 1 we can write it as s square. Okay, let me write this. From equation 1, if we take common m, then we'll have b by ms plus k by m equal to 0. Okay, also we know the equation, second order equation for the systems where zeta is damping coefficient, or damping ratio. Omega n is the natural frequency of the system. So if you compare these two equations, so compare equation 1 and if you compare this, you will get, first we will compare the omega n terms. So omega n square is k by m, or we can write it as omega n. For this mechanical system, which is natural frequency, is under root of k by m. Okay, now we have equated these two terms. Now we'll equate these two terms. So 2 zeta omega n is b by M, or zeta is B by 2 omega n m. If we put the value of omega n in this equation, we get 2. This is k times m, or we can write it as zeta is b to under root of k multiply by with m. Now we'll see the quality factor. So the quality factor of this system, we have denoted it with Q is omega naught m, or first we will write in terms of zeta. So the quality factor can be written as 1 by 2 times of zeta. Now if we put the value of zeta in this, zeta is b times 2 omega n, and this 2 and 2 is get cancelled. So the Q quality factor can be written as omega n m by b. Or we can write this in other way as theta is 1 by 2 times of quality factor. Both way we can write this. Now if they asked what is the natural what is the period of this natural frequency, what is the natural period, Tn, this is 2 pi by omega n. Okay, or we can write it as 1 by fn, which is period for natural oscillation. Now the frequency of the oscillations can be write it as Fn which is 1 by 2 pi times of k by m. The frequency of is a natural frequency f n for the system. Now we'll see some stability conditions. Stability check. Okay. Usually we'll check the stability of any system with zeta value. So suppose first system can be a four type: overdamped, second one is critically damped, third one is underdamped, and the last one is undamped or zero damping. So we'll see one by one. If the value of zeta is greater than 1, then the system is called as overdamped system. So we'll calculate first. The procedure would be first we'll calculate the value of zeta, and then we'll see if the calculated value is greater than 1, then directly we can say that the system is an overdamped system. Okay. Now, if for the critically damped system, if the calculated value of zeta is equal to 1, then we can say the system is critically damped. Okay. Now, if the value of zeta is less than 1, then system is called the underdamped system, and if the value of zeta is 0, this is called zero damped system or undamped system. So this is the way to calculate the stability, to calculate the value of zeta, and uh, by using this zeta we can say whether the system is overdamped, critically damped, underdamped or undamped. This is the way to say this. So for the critically damped system, usually the response is like this. After some time, it will settle. For underdamped system, The response is something like first it will have some transients, so it will oscillate. Then after some time, it will settle. Okay. Now for overdamped system, the response is very smooth. This is overdamped system, and for the undamped system, the response is something like that. The system will not get stable. It will always oscillate at this condition, at this way. So this is the response of different systems. So now I'm going to summarize today's lecture, today's tutorial session. So for today's session, first we have start with spring mass system or sensitivity of the accelerometer. Sensitivity. Okay. So we have seen the sensitivity of the accelerometer, which is a measure of displacement in terms of acceleration, or we can write it as m by k. Now then we have seen some different kind of pressure sensors: absolute pressure sensor, gauge pressure sensor, and differential pressure sensor. So in case of absolute pressure sensor, we usually measure the pressure related to the vacuum. In case of gauge pressure sensor, we measure related to the atmosphere, means the reference is atmospheric pressure. And in case of pressure sensor, we measure pressure which is different from two pressure sensors. So we fix one pressure sensor as a reference, and then we'll measure the difference between these two pressure sensors. Then we have seen the how we'll calculate the pressure using the formula based on the plate theory. Then we have seen this equation can be written in terms of linear equation if the value of W naught H is too much less than 1. Then this equation shows a linear relation with pressure and deflection. Then we have seen some piezoresistive sensors. Then stress for longitudinal. Then we have also seen burst pressure, which is the maximum operating pressure, or we can say that a material can withstand a maximum stress at the can withstand with maximum stress at this pressure, which is 5 times of operating pressure. We usually operate at this point, and we can't exceed this limit. Okay. Then we have seen some formulas like how we'll calculate the maximum strain. Then gauge factor, which is a change in resistance if the value of strain changes. So it is a measure of uh, it shows the changing property of the material. Then we have solved some problem based on this piezoelectric sensors. What happens if we apply longitudinal force? Then what happens if we apply force in the transverse direction at the midpoint of the cantilever beam? We have calculated the change in resistance for both the condition. Then we have calculated the burst pressures, burst pressure and the maximum operating pressure. Then we have solved some true false problem. And then in last we have seen some problem for the accelerometer. So I'm stopping. So I'll stop here. So guys, if you have any doubt, you can ask me, or you can email me. My email ID is Vaishali 22 at the rate icerb.ac.in. You, if you have any doubt, you can mail me or you can directly ask me. Thank you. Thank you for today's session.
Thank you, ma'am.
Thank you.